Just again, I talked about this briefly yesterday too, that the first thing we do in a scoping is to look at all the potential sources of water and all the potential uses. So instead of being myopic about we want to capture the rooftop rainwater to irrigate, we want to capture rooftop water maybe just to flush toilets, we try to get that discussion going early about other potential sources, other potential uses, so that we're really maximizing the potential of that system overall as opposed to just making a rainwater harvesting system. So there, beyond rainwater, there is surface stormwater, there is greywater from showers and sinks, there's that condensate coming from the cooling systems, there could be groundwater being pumped out of the foundation area, really a number of possible sources that we can tap into. And then we take a look at all the potential uses of that water. It could be rooftop, it could be irrigation, it can be toilet flushing, it can be cooling tower makeup, it can be boiler makeup. Any one of those are prospects for a building that can be incorporated into the design early on. With the net effect being that we're trying to maximize month by month as best we can the total use or total demand for non-potable water and the total supplies that we have available for it. All right? Every system that's being designed, regardless of what kind of system it is or how large or how small it is, has 4 basic components, and I want to take you through that so you can kind of see how we mix and match those in a custom system. There's first of all the primary filtration storage. So we have that water source coming from someplace. We have to do some kind of initial cleaning of it so it goes into our cistern in a clean state. We're storing that water, and there's lots of options for storing. We'll talk about those. And then there is virtually always a sanitation stage here. We want to stabilize that water for storing it. We want to make sure we don't have any algae or bacteria growth or other kinds of issues with the water while it's being stored. We want to make sure it's safe for reuse, particularly in commercial buildings. You know, you've got the public at stake here. You've got exposure to the public, whether you're spraying for irrigation or flushing toilets. We want to make sure that water meets safety standards, and so there is a sanitation step of some sort. Then finally, we have a last kind of a polishing step of that water. We want the water to be clean. We don't want to have sediment in the toilets. We want to make sure that the water is then pressurized to meet the requirements of the building. So now we're balancing the pumping and pressurization system with, let's say, the number of toilets or the kind of irrigation system it's got. So there's that last step. And then all that's being controlled by a sophisticated system that's actually monitoring the system. It's measuring the amount of water being captured. It's deciding when to switch from harvested water to municipal water if they need to. It's able to tell us the status of filters, the status of the chlorination system. So we're talking about a commercial system with commercial controls with everything being monitored and managed. Okay? So let's go through some of those components. You'll see how that works. The initial primary filtration storage, it depends on the source of water. If we're talking about rainwater or stormwater, it can be done organically. And there's a lot of, you see this happening now pretty commonly, these vegetated swales, we're capturing water, we're filtering, we're doing some biofiltration. That's great. I mean, we're not in that business, but we certainly encourage that kind of natural filtration of water, first of all. More commonly, particularly with rainwater, we're talking about as a first flush system, so it's able to detect a rain event and divert the first few minutes of water into the storm system, and then that water it's pretty much flushed the roof of the building, and so now the water comes into the cistern directly. More commonly are the vortex filters for rooftop rainwater. You've seen these, they require no maintenance. It's basically a vortex with a hole in the bottom of the funnel for the debris to drop through. And that gets the water down to about 200 microns in size. So we're getting most of the large debris out of there and particulates, and we're capturing about 95% of the water coming off that rooftop into our cistern with a zero maintenance kind of a filter, which is of high interest to most building owners. They don't want to deal with changing a basket filter every time it rains. There are other methods as well, but those are probably the most common. And then we have to think about how we're going to store it. And storage really is kind of the number one decision in most of these systems because it's high cost and has a lot of impact on the space we're going to have for the building and where that water is being stored. We say we're storage neutral, that we don't care what kind of storage it is, and we really work with the property to decide what the best storage is. In some cases, for greywater, for instance, where we have a good supply and demand match, the storage can just be polyethylene tanks in the utility area. These are 200 or 300 gallon tanks, so we've got maybe a couple of thousand gallons of storage there. We can do underground storage in concrete vaults in a typical way. Large fiberglass tanks can be used. They're pretty expensive, but that's another alternative to get the water out of sight, out of mind, if you would, and not taking up valuable space inside the building. We're very high on the underground Atlantis system. This is, you guys are familiar with this? These are the recycled polypropylene boxes, basically, that are constructed on site. They're very lightweight. They're 90-some-odd% recycled material. They are buried below ground in any kind of shape you need. So you can go low and long and flat. You can go deep and shallow. It can shape around foundation if it needs to, around utilities. So it's a very flexible storage, very inexpensive. It's probably a third of the cost of a fiberglass tank. And then that tank can also be set up for infiltration if you need to. We're part of it. So we're real high on this. We think it's a real good solution, and there's the water is kept in a really clean state as well. There's some bio action going on with that water, so it can't turn septic in that system, which is good. Here's a typical Atlantis application. The water's being pre-filtered through a vortex separator here, going into the tank. The tank is buried. The excavation is lined with like a pond liner, a heavy polyethylene liner that keeps the water in. The tanks themselves are wrapped in a geotextile, which serves as a filter for the overall tank. And then we compact sand around that tank to stabilize it, and also to serve as a biofilter. So we have the water in the tank can then pass through that membrane into the soil around the tank. And we actually have a bioaction helping to keep the water clean and oxygenated and fresh. So it's a really cool system, really good approach overall. These are above ground steel tanks. These are CoreGal tanks. These tanks can be anywhere from 700 gallons to 600,000 gallons. They can be very large. A lot of architects like these. They've got an architectural feature and element to them. They're also above ground, so you don't have to worry about high water tables, that kind of thing. They can be, like I said, we use several small tanks or one large tank, so they're very flexible in the kind of size we have. So that's a good option as well for storage. After the water's been stored, we now are going to start processing. This is just a quick chart kind of showing the major components of a cistern and the plumbing of that. And I'm not going to go spend a whole lot of time on that, but really it's just a way of keeping the water, getting the water out of the tank. You guys are familiar with RPZ valves. We always have a system to prevent backflow of our harvested water back with the municipal water. Many communities now are requiring air gap fittings, so most of our systems employ that. We use a day tank, and we have an air gap into the day tank, so we have no chance of a backflow situation. And we find that while RPCs are acceptable in some communities, the air gap is always preferred, so we do tend to use that in our systems when we can. The next step would be water sanitation stabilization. So if we're storing that water for a period of time, we want to stabilize it. We want to make sure that when the water is being reused, it is sanitized. Two primary methods that we use are either chlorination. Here you're seeing this. This is a hypochlorite system. So it's we like this. It's a pellet system. So you take these briquettes of chlorine, kind of like a pool chlorine. They're put into a hopper. Water is sprayed on that and creates a high concentration of chlorine that's being used. And then we dose that and measure the amount of residual chlorine in the system to be able to apply enough chlorine to kill whatever bacteria there might be, viruses, that kind of thing. Yes?
If there was a jurisdiction that required that the reused water be colored blue, like some jurisdictions,
Yes.
This is where you would add that coloring?
We would do that in the day tank. So we would pump the water from let's say we have a 25, 30,000 gallon cistern below ground. We pump out of that cistern into a smaller 200 gallon tank. We'd chlorinate in that tank. We'd also add the blue dye in that tank. Yeah, there are some communities that do require blue dye, and so we add that as well.